Hi, everyone. This is the second part of the EC'21 tutorial on profit inequalities and implications to pricing mechanisms and online algorithms. The first part was given by Sahil Singla, and now I'm going to do the second part, and the third part will be given by Thomas Kesselheim. And this part will be on profit algorithms specifically for graph matching. Oops, doesn't. Okay. So I'll do a really short introduction to profit inequalities for those of you who just joined. So profit inequalities are algorithms for online scenarios that can be viewed as type of push your luck scenarios, like when you have to make a decision about a job offer or a ride or choosing a secretary or an Airbnb apartment or even a partner for life. In all of these scenarios, you have to make an online decision, meaning that you have to make a decision now based on the information you've seen so far and without knowing the future. And this is part of what's called optimal stopping theory, where the basic model is where you have a sequence of n values, v1 to vn, which are initially unknown, and the values are revealed online, one per round. So maybe the first value is 10,000, and you have to make a decision now, and the decision is immediate and irrevocable. You can either stop, in which case you take the $1,000 and go home, the game ends, and you win $1,000, or you decide to continue, in which case you lose this prize forever, and the game continues with the next box. So maybe the next box is $4, and then 10 to the 6, etc., etc. This is a worst case scenario, and it's not very difficult to see. And in fact, Sahil showed you in the first part that in the absence of additional information, there is not much that can be guaranteed. So in order to deal with these situations, what's really very common in life is that you have more information. These are beyond worst case scenarios. And one very common model, which is the focus of this tutorial, is called profit or profit inequalities or profit algorithms, where the extra information you get, the beyond worst case part, is that you know the underlying distributions. So maybe the arrival order is still worst case, but the underlying distributions for your values are known. And as those of you who have seen Sahil's part, you've seen that a lot of impossibility results can be overcome by this extra information of knowing the underlying information, the underlying distribution, sorry. The other model, which is not going to be part of this tutorial, I'll just mention it from time to time, I just want you to know about it, is a secretary model, where the values now are adversarial. We don't know the underlying distribution. They're not assumed to be drawn from any distribution. They're just adversarial. And the extra information we have is that the arrival order is random. So you can think of an adversary who chooses values adversarially, and then nature reshuffles the values and they arrive in random order. And this is also beyond worst case. There are nice things you can do with this extra information. Great, so what's the model? Let's be more formal about the model. You have n values that arrive online, v1 to vn, and the arrival order is pi. An algorithm, possibly a randomized algorithm, is a stopping policy. When do we want to stop and take the prize offered to us and go home? And alg v pi is the value accepted by algorithm on the sequence v under arrival order pi. And let's also denote by opt v the maximal value on v. And a very common performance measure in online algorithms is the competitive ratio, which is the ratio between the performance of my online algorithm and the performance of the optimal solution, had I known all the information. So let's formalize the competitive ratio for the case of profit inequalities. So the competitive ratio, which I denote here by rho alg, the competitive ratio of an algorithm alg. So in the numerator, I have the expected performance of my algorithm. I take the minimum over all arrival orders pi, because this is, remember, worst case order. And then I take the expected value that the algorithm gives me on pi. And the expectation is with respect to the underlying distribution D. By the way, let's also assume, and throughout the whole talk, we will assume that all values are drawn independently at random. So VI is drawn from a known underlying distribution, DI. So this D is a product distribution. So this is the performance of the algorithm. And the performance of opt is just the expected value of opt. In this case, it's just the expected maximal value. Okay, and let me just say very briefly what's the competitive ratio in a secretary model. So in a secretary model, I take the minimum over all values, those are chosen adversarially, and then I take the expected performance of my algorithm, where the expectation now is over the arrival order, which is random, pi is now random, and I divide it by opt v, and now there is no expectation, it's just the maximal value. Okay. So let's, just we can play, but we'll do it really quickly because this is just repeating what Sahil showed you. So this is a scenario that you should have in mind. I tell you, and let's even tell you, I tell you the order in advance. So maybe the first value is drawn uniformly from 20 to 40, and then the second one uniform 2040, third one uniform 1050, and the last one uniform 070. And then I just tell you, okay, the first value is 33. Do you take it or not? Okay, so I could have played it with you. I won't do it for the sake of time. You have to decide if you take it and go home or continue to the next round. Okay, you can think for yourself whether you take it or not. And then those of you who haven't taken it, now do you take the 22 and go home? And if you didn't take that, do you take the 36 and so on and so forth? And the goal is to maximize the expected value that you get. So what's known about the competitive ratios for these scenarios? For the profit, we have a fixed threshold algorithm that gives half, just like Sahil showed you. And I'm going to show you, now I'm going to concentrate on, so Sahil mentioned there are two different ways to choose the threshold. One is the mean, the other is the median. Each one has its own advantages and disadvantages. By the way, any value in between would also work. I'm going to focus on the mean threshold because I would like to show you how it generalizes nicely to matching scenarios. And I should also mention very briefly that for secretary, and this half is tight. And for secretary, that we can do 1 over E, and this is also tight. And the way to do the secretary algorithm is by explore exploit, where you just observe some initial elements in the beginning, because all that plays for you in the secretary scenario is that the values arrive in a random order. So you want to take advantage of this random order. The way to take advantage over the random order is to do some observation in the beginning, and then it's again threshold based. You set a threshold. You set the threshold to be the maximum value observed in the exploration phase, and then you accept the first value that exceeds that. Okay, so these are two threshold-based algorithms, one for the profit model, which is the focus of this tutorial, the other for the secretary. For profit, we get 1/2. For secretary, we get 1 over E. Okay, and now let me show you a natural economic interpretation of this scenario. So suppose we have a single good for sale and the agents 1 to n arrive sequentially. The value of agent T, VT, is drawn independently at random from distribution DT. And the seller posts a price tau and sells to the first agent whose value exceeds tau. Now, because of the threshold algorithm that we showed you for profit inequality, a direct corollary is that setting a price to be, in this case, I choose mean, which is half the expected optimal value, obtained at least a half of the optimal welfare. And I'm going to show you the proof, which is essentially more or less just the same proof that Sahil showed you, but I want to show you the proof using a different terminology, which is a decomposition. So essentially what we are doing here can be, in this scenario of a market scenario, it can be viewed as welfare maximization. We want to maximize welfare, meaning we want to sell to the agent with the highest value. And the way to set the bound on the welfare is by decomposing welfare into revenue and utilities. Okay, so here is the proof. So the theorem says that setting a price tau to be half the expected maximum yields welfare at least half the expected maximum. This is a cute coincidence. It's just, you know, the threshold itself gives you exactly the guarantee. But as we've seen, there are other thresholds that give the same guarantee. So this is just a coincidence. And let me repeat the proof using a different terminology. So let V star be just maximum value. This is a random variable because those values are distributed according to known distributions. And now I'd like to decompose welfare. And welfare is just the sum of the revenue obtained by the seller and the surplus of the agents, which is the sum of utilities of the agents. What's the revenue of the seller? The revenue of the seller is tau, the price, times the probability that the item is sold. Okay, if you recall Sahil's proof from before, this was the benchmark. Like if there is a value that exceeds the threshold, you get it. And then there was some extra stuff, which is going to be the surplus that I'm going to show you. So the revenue is tau times the probability that the item is sold. What's tau? Tau is half the expected maximum times the probability that the item is sold. Now let's do the surplus. So what's the surplus? The surplus is the sum of all agents' utilities. Using linearity of expectation, it's the sum over all agents I of the expected utility of buyer I. Now, because we know that agent I, when agent I arrives to the market, she maximizes utility, we know that this expected utility of buyer I is at least the expected of VI minus tau plus, meaning the maximum between VI minus tau and 0, because if VI exceeds tau, buyer I can buy the item, times the indicator variable for the event that I sees the item. Maybe by the time that I arrives, the item has been already taken. Now I use the fact that those values are drawn independently to express this as the expected of VI minus tau plus times the probability that I sees the item, because the event that I sees the item is independent of I's value. Okay, and now this is at least the same expression, but now I can replace, I do greater or equal, and I can replace the probability that I sees the item by the probability that the item is not sold, because if the item is unsold, of course, it's unsold before I. And now I just replace sum by max. This is, I think, a really interesting transition because it seems really lossy, and still it gives us the tight result. And as you've seen in Sahil's part, you see that the worst case scenarios are ones where you get all the value from a single element. That's why you don't lose when you move from sum to max. And of course, we use again linearity of expectation. And now this is greater or equal, but then half the expected maximal value times the probability that the item is unsold. This is just by substituting tau by the definition of tau. And now I do this decomposition of welfare equals revenue plus surplus, and I see that revenue is half expected max times the probability that the item is sold. The surplus is at least the half the expected max times the probability that the item is not sold. And together we get that the welfare, which is the revenue plus the surplus, is at least half the expected maximal value. And this concludes the proof. Okay, so the reason I showed you this again is because I'm going to generalize it soon to matching scenarios. By the way, a disclaimer about the rest of the talk. These slides cover more than I plan to say in this tutorial. They are longer and I do not plan to cover them all, but I'll leave all these slides on the tutorials website in case some of you want to get more details after this tutorial. Okay, and now, as Sahil said, we can generalize these profit scenarios beyond the very classic scenario of choosing a single item to combinatorial feasibility constraints. So in these scenarios, we are given a collection of feasible subsets of elements, and we can accept any feasible subset, and the goal is to maximize the sum of values of accepted elements. So this has been studied a lot for matrices, for knapsack problems, for downward closed scenarios, for combinatorial auctions, and the focus in this part will be matching in graphs. Other parts have already been covered by Sahil, and some parts like combinatorial auctions will be covered by Thomas. Okay, so matching in graphs, this is going to be the focus of this part. Matching in graph is a very fundamental model with numerous applications. Just to mention some, think about items and buyers in e-commerce applications, or drivers and passengers in ride-sharing platforms, or ad slots and advertisers in online ad auctions, and jobs and workers in online labor markets, and many more scenarios, given the huge range of applications these days. These problems come in two flavors, edge arrival and vertex arrival. Now, let me stress that in these models, we think of the elements that arrive online are the edges. In both scenarios, the elements are the edges. In the edge arrival model, it's just like the profit model, the classic profit model, in the sense that the elements, which are the edges, arrive online, and we have to make immediate and irrevocable decisions. We see the elements one by one. The other model is vertex arrival, where in every step, some vertex arrive, and what we observe is the realization on all the edges that are adjacent to this vertex. So this can be viewed as a batched model. This is not the classic online model where elements arrive one by one. In this case, in the vertex arrival model, the elements arrive in batches, which should be helpful. And then we will see, and as we will see, it is helpful. We see more information at once. And the batched model makes sense when there is a natural interpretation, like in graphs, where the natural interpretation is that some vertex arrive and you see all the edges adjacent to it. And the goal is to maximize the total weight of the chosen matching. Okay, so let me start by the model of matching with vertex arrival. And we will concentrate now on one-sided matching in bipartite graphs. So here is the model. Think of a bipartite graph where maybe think of the left side as agents and the right side as items. This is one-sided arrival, meaning that the right side is static. The items are just static in the market. They're always there. The dynamic side is the agents. The left side, those are the vertices that arrive online. So we have a weighted bipartite graph, G, which is composed of the left part, the right part, and the edges, E. Every edge E has a weight WE, which is drawn from distribution DE independently. And initially, we don't know the weights. The WEs are unknown, but we do know the underlying distribution, just like here. Maybe we know that the top edge is uniform 0.3, and the next one is Bernoulli 0.5, etc., etc. And upon an arrival of a vertex V from the left side, remember the vertices on the right side are static, the vertices on the left side are dynamic. Upon the arrival of a vertex from the left side, the weights of its edges are revealed. For example, maybe the first vertex to arrive is this, and remember, we don't know the arrival order up front. Once this vertex arrives, we see the realization of all the edges that are adjacent to this vertex, And we need to make a decision whether to match this vertex, and if so, to whom. So we already see that this is a more complex decision that we have to make, not only whether or not to choose it or to choose this, to match this vertex, but also using which edge. So maybe we can choose this edge and then the next vertex arrived, and now the edge adjacent to it is revealed. We cannot choose it because we can only choose a matching and its neighbor is already taken, etc., etc. This is the setting. Okay, so what do we know about this setting? What I'm going to show you is a profit algorithm that gives a half. And okay, I'm going to cover, so let me skip this part because I'm going to cover it in detail, including the proof. Let me just tell you that there is a really beautiful paper by Thomas Kesselheim and Radke, Tonis, and Focking from 2013 that shows that the same 1/E competitive ratio that can be obtained for the secretary model, the other model, not the profit model, so for let me remind you, in the classical secretary model, we can get 1/E, and this is tight using an explore-exploit technique. And what this paper, so the first paper that studied this problem was Korula-Pal 09. They showed some constant ratio, and then Kesselheim et al. Improved it to 1/E. And the way to obtain this tight 1/E result is to, again, observe some initial elements without accepting any of them, just like the classic secretary, the right observation length is N/E. And then on each round thereafter, you consider the optimal offline solution on the observed input so far, and you match the arriving vertex to its partner in the optimal offline solution if its partner is available. This algorithm gives you 1/E. The algorithm that I'm going to show you soon gives 1/2 for profit. So interestingly, we moved in both models, both profit and secretary. Those are two beyond worst case models for online algorithms. The classic result, the classic scenario, which gives 1/2 and 1/E, which is tight, extends exactly the same to a much more complicated scenario of one-sided matching in bipartite graphs. So let me cover the proof for this by one-sided matching in bipartite graph. So again, we will consider it as a market scenario with agents and items. We set a price tau u to every vertex u on the right side. So these are my items. I just set fixed price to every item. Upon the arrival of a buyer V from the left side, buyer V chooses an item that maximizes her utility. What's her utility? It's the difference between her value for the item, which is the weight on the edge VU, minus tau u, the price of the item U. And buyer V chooses an item U that maximizes this utility among all available items. Some items are not available anymore, or it can also just not choose anything if the utility is always negative. And by the way, this is the special case of a single item is precisely the threshold algorithm that we've seen for the classic profit inequality. Interestingly enough, the same thing holds for the secretary problem, where the paper of Kesselheim et al. That I just mentioned can also be perceived as a generalization of the classic scenario. So what's the theorem here? The theorem here says that setting a price, so remember now we just set fixed prices for all the items, and the theorem says that if we price every item U to be exactly half of its expected contribution to all, okay, observe that this is again a generalization of the classical setting, then we observe at least half of the optimal welfare. And let me show you the result, the proof now in detail. And the proof again goes by this decomposition of welfare into revenue and surplus. what I'm going to show you is that the welfare that equals revenue plus surplus is at least sum over all items U, tau U. This is the price of item U, which is by definition of tau U half the expected optimal value of the matching. Okay, good. So what's the revenue? The revenue is the sum over all items U of the probability that item U is sold times the price of U, tau U. What's the surplus? Okay, so for the surplus, I just need to move the window with all the faces. Okay, so here is a claim. For every distribution lambda over the items, so this claim says that the utility of agent V are the vertices on the left side, which are the agents, is at least the following expression. So let's look at this expression. What does it say? So the claim is, what the agent can do is just fix some distribution lambda over the items. And then when agent V arrives to the market, agent V knows WV, which are all the weights on the edges adjacent to V. It can choose an item according to the distribution lambda and pick this item if the item U is available and it obtains a non-negative utility from this item. Okay, so this is exactly the expression that is written here on the right-hand side. Therefore, the utility of V is at least this expression. And we can take, for example, this distribution lambda U to be exactly the distribution PVU, which is the probability that V is matched to U in the optimal solution, given WV, given the weights on all the edges going out from V. So now if we take this distribution, now all we need to do is sum over all agents V, okay? Because remember, surplus by definition is just the sum of the agent's utilities, and take the expectation over the weights W. And what we get is that the surplus is at least this expectation over W of the sum over all agents V. And for every agent V, we know that its utility is at least this expression. And now we use again the fact that the probability that U is available at V, meaning when V arrives, is at least the probability that U is not sold at all, of course, because if U is not sold at all, of course, it's available for V. Now we just rearrange this expression. And finally, all we need to do is to observe that this orange expression here is just the expected contribution of item U to the optimal matching. Okay, because this is how we chose lambda to be PVU. This is exactly the probability that U is matched to V. So this orange expression is exactly the expected contribution of item U to the optimal matching, which is by definition of tau U of the pricing we chose, 2 times TU. So now if we look at this expression, this is exactly the sum over all items U of the probability that item U is not sold times tau U. So now what we see, just like in the classical case, that the revenue is the sum over all items of the probability that item U is sold times tau U, and the surplus is at least the sum over all U of the probability that item U is not sold times time U. So together we get exactly the desired inequality here, that revenue plus surplus is at least sum over U of tau U, which is half the expected optimal matching. And this concludes the proof. Okay, so this proof shows you how we generalize the same mean threshold from the classical setting to this other mean threshold in the much more complex setting of matching in bipartite graph to get exactly the same result. Okay, now in the next part, I would like to do the other arrival model, which is edge arrival. In this model, again, we are given a weighted graph G. And by the way, in this part, I do not assume, although the picture here is of a bipartite graph, the results here are not specific to bipartite graph. It can be any general graph. So we are given a weighted graph G equals VE, not necessarily bipartite. Just like before, every edge E has a weight WE, which is distributed independently from DE. Initially, all the WE are unknown and the underlying distributions are known. Now, the edges are the arriving elements. Before, the vertices arrived online. Now the edges themselves, the elements themselves, arrive online. Upon the arrival of an edge E, its weight WE is revealed. And the algorithm decides whether or not to include E in the matching. So for example, maybe this edge just arrived, I see its realization, which is 7, and I have to make a decision whether to take it, to match it or not. Maybe I chose not to. Then the next edge reveals itself, this is 1. Maybe I choose to include it in the matching, and so on and so forth. Okay, and you can already see that, of course, edge arrival model is more difficult than vertex arrival model, because in the vertex arrival model, I can just mimic the edge arrival model. I have more information at one stage. And to solve this problem of matching with edge arrival, we use a different approach than the threshold approach that I showed you before, which is known as online contention resolution scheme. And to introduce this very nice approach, I would like to go back, before going to matching with edge arrival, I would like to go back to the simple single element scenario. By the way, important to mention that the Feldman in the reference here is not me. It's also M. Feldman, but it's not me. Okay, good. So online contention resolution scheme. For simplicity, let me suppose the result is completely general for general distributions, but just for simplicity, for the sake of this tutorial, let me assume that the distribution is just Bernoulli, very simple. Wi, which is the weight of element I, remember no matching now, it's just the classic setting of n elements that arrive one by one, and the weight of item I is xi with probability pi and 0 otherwise. Okay, a very simple distribution. The first lemma is that the profit, okay, the expected max Wi, which is the profit, is at most bounded above by the following linear program. The linear program is max sum I yi xi. Okay, yi are the variables that we have here. Xi is the parameter. Let me remind you that the distribution we are using is that Wi equals xi with probability pi and 0 otherwise. So xi and pi are our input, and the yi's are the variables. So what's the LP? What's the linear program? We want to maximize the sum over I of yi xi such that sum I yi is at most 1. And sorry, it's not for every I. That's a typo. And for every I, yi is between 0 and pi. And the claim is that this is an upper bound on the profit. Why? Because we can simply set yi to be the probability that I is max when we restrict ourselves to choose only non-zero values. This is a feasible solution, and it equals exactly the profit in this scenario. So we know that the profit is upper bounded by this program. Okay, so now let me show you an algorithm that gives at least 1/2 of this LP. So the algorithm is very simple. Upon arrival of element I, if Wi equals xi, so we observe the realization, we know whether it's xi or 0. If indeed it's xi, then we pick element I with some probability. What's the probability? The probability is yi, this is the solution from my LP, over 2 times alpha I pi. Pi, remember, is part of my input. This is the probability that Wi equals xi. And alpha I is 1 minus 1/2 over the sum of all j that arrived before I, yj. Okay? The way to think about it is that I do some hedging. I don't just pick an element if Wi equals xi. I only pick it with some probability. And the probability is precisely this. And we'll see that this probability gives me the half approximation ratio. Okay, and by the way, as we will see, and we will prove by induction, is that this alpha I is precisely the probability that element I is reached. Let me do the analysis, because it's simple enough to show it in the tutorial. So first of all, I need to show you that this is a valid algorithm. To show you that this is a valid algorithm, I need to show you that this probability, yi over 2 times alpha I pi, is indeed smaller or equal than 1. Why is this the case? So first of all, this probability is at most 1 over 2 alpha I, because yi by the LP is at most pi. This is the red transition. Now, to do the green transition, I just need to show you that alpha I is at least 1/2. So let's move here to the green explanation. What's alpha I? Alpha I, by definition, is 1 minus half the sum of yj for all j that arrive before I. And this is at least 1 minus 1/2 of the sum of all j yj, which by the LP is at least 1/2. Okay? And now I want to show you that every element I is picked with probability exactly yi over 2. And the whole idea of doing this hedging, this choosing element I only with this probability, is to make sure that I actually pick every element exactly with probability yi over 2. And the proof is by induction. So suppose by induction that this holds for every element j smaller than I. Now, what's the probability that I pick I? The probability that I pick I is the probability that I is reached times the probability that Wi equals xi, because remember, my algorithm chooses an element only if Wi equals xi, times this probability, this blue probability, yi over 2 times alpha I pi. What's the probability that I is reached? By the induction assumption, this is precisely alpha I, because by the induction assumption, every element before is chosen with probability yj over 2, so alpha I is precisely the probability that I is reached. What's the probability that Wi equals xi? That's exactly pi. So now when I multiply these 3 expressions, I get exactly yi over 2. So now the expected performance of my algorithm is sum I of Wi over 2 times xi, which is at least 1/2 of profit by the lemma above. Okay, because we know by the lemma that the profit is bounded above by sum I yi xi. Okay, so this is a pretty simple proof for the classical scenario. And the beautiful thing about this approach is that we can generalize it quite easily to show that we can obtain 1/3 approximation for graph matching with edge arrival. So let me spend the remaining time to show you this proof. So again, we are going to do an OCRS approach for graph matching with edge arrival. And we're going to show 1/3 approximation. Just like I told you before, remember that for vertex arrival, we get more information at one step, and indeed it's helpful. We can do 1/2 approximation. Whereas for edge arrival, we cannot do 1/2. What I'm going to show you now is that we can do 1/3. In the paper that is cited here, we actually show that we can do better than 1/3, but this proof is more complicated and I'm not going to cover it here. But we also know from a different paper, not ours, that we cannot do 1/2. Okay, so indeed there is a gap between what can be done for edge arrival and for vertex arrival. Good. So again, for simplicity, let me suppose that every edge E has weight XE with probability PE and 0 otherwise. Again, the real proof in the paper doesn't use this assumption. This is just for simplicity, because my main goal here is to show you what this OCRS approach is all about. Good. So the proof will be very similar to before. The first lemma says that the profit in this setting, and what's the profit in a matching setting, is the expected value of the maximum matching. And the lemma says this is at most the solution to this linear program. What's this linear program? It's the sum over all edges E of YE times XE. What are our constraints? For every node U, we want the sum of all edges E such that U belongs to E of YE to be at most 1. This is matching. And also for every edge E, we want YE to be between 0 and PE. So now let me show you the algorithm, which is very similar to what we saw before. Upon the arrival of an edge E, some edge E UV, if WE equals E is available, what does it mean that E is available? It means that both its end sides, U and V, are available by the time edge E arrive. Maybe one of them is unavailable, maybe both of them are available. But if WE equals XE and E is available, then we want to match it, but not always. Just like before, we do this hedging. We only match it with probability YE over 3 times alpha E PE, where alpha E is the probability that E is available, which we need to calculate. Okay, so we calculate for every edge E upon its arrival, what's the probability that E is available, and we match it with probability exactly YE over 3 alpha E PE if WE equals XE and E is available. And as I'm going to show you, the way to choose this probability is to make sure that every edge E is picked exactly with probability YE over 3. So this will give us 1/3 approximation with respect to this upper bound on the profit, and of course on profit with respect to the profit itself. Let's do the analysis quickly. Again, very similar to the previous one. So what's the probability that E is matched? The probability that E is matched is the probability that E is available times the probability that WE equals XE times this probability WE over 3 alpha E PE. What's the probability that E is available? That's alpha E. The probability that WE equals XE is PE. And now we multiply these 3 expressions to get exactly YE over 3. Now remember, one thing that I need to show you is, in order for this proof to be valid, is that YE over 3 times alpha E PE, this expression here, is indeed smaller or equal than 1. Why is this true? And again, we are doing it by induction, just like before. So again, the first transition is because YE is at most P. That's by the LP. So now all that left to do all that left to show is that alpha E is at least 1/3. Okay, what's alpha E? Alpha E is the probability that E is available. We use a simple union bound to show that alpha E is at least 1 minus the probability that U is unavailable minus the probability that V is unavailable. So let me mention that this union bound makes the proof very simple. And if we just use this union bound, we get 1/3, as I'm going to show you. If we do a more complex inequality here that uses the correlation between the events that U is unavailable and V is unavailable, we can slightly improve to get a better bound than 1/3, but I'm not going to show it here. Okay, so now, what's the probability that U is unavailable? And the same holds for V. It's the sum over all edges E prime smaller than E such that U belongs to E prime of the probability that E prime is matched. And now, by induction, we know that the probability that E prime is matched is exactly Y E prime over 3. So we get that this probability is at most 1/3. And overall, we get that alpha E is at least 1/3 as desired. And together, we get that the expected value of my algorithm is sum over E of YE over 3 times XE, which is at least 1/3 of. Okay. And this is the end of this proof. So this is a very simple proof that uses the OCRS approach that shows 1/3 approximation for edge arrival. Let me also mention, I forgot to add this reference here, but there is also a threshold-based algorithm by Graving and Wang showing this 1/3 approximation for this model using a threshold approach, not an OCRS approach. But as I mentioned, with this OCRS approach, one can do better than 1/3. So this is actually the part that I'm not going to cover, but I'm going to just leave it on the slides if you want to go over it later. So just to mention that we can also use the OCRS approach to do graph matching with vertex arrival for general graphs. So remember, before I showed you that with threshold-based approach, we could do 1/2 approximation for one-sided bipartite matching with vertex arrival. We could do 1/2 using threshold base. And this result shows that we can take an OCRS approach to obtain this same 1/2 result for general graphs. So in this model, so again, this picture is of a bipartite graph, but it works for general graphs. So in this general graph scenario, we have a general graph, vertices arrive online in an unknown order. Every time a vertex arrives, I see the realization of the weights on all each edges to previous vertices. And again, the goal is to maximize the expected size of the matching. And currently with OCRS approach, we can do 1/2 approximation again. It's still unknown whether there exists a threshold-based algorithm that gives 1/2 for this problem. So let me skip, I'm not going to cover this algorithm and analysis. This will be part of the slides if you want to review it later. And I'll skip directly into the summary. Right. So in this part focused on profit inequalities for graph matching. And as we've seen, there are 2 main approaches for doing online algorithms in profit model for graph matching. One is threshold or pricing approach. And what we've seen is 1/2 approximation for one-sided bipartite matching. By the way, Thomas Kesselheim in the next part is going to show a very nice generalization of this result that goes way beyond matching to general combinatorial auctions. And we've also seen an OCRS approach, and using an OCRS approach, we can do 1/2 approximation for matching in general graphs with vertex arrival, and 1/3 approximation for matching in general graphs with edge arrival. Thank you very much.